Good morning. I have some very exciting news to share with you guys today. We are starting Unit 9, and Unit 9 is all about the behavior of gases. So, gas laws are really interesting to study. It's a lot of math, and I do believe it's a very logical topic. So, the first thing that we want to talk about is what makes gases different than the other states of matter, solids and liquids. And the main difference is that gases are compressible. So compressibility may or may not be a word that you've heard before, but what compressibility is it's a measure of how much the volume of matter decreases under pressure. So you can put as much pressure as you want on a solid substance or even a liquid, and that volume isn't going to change much. But gases are able to be compressed. So think about squeezing a balloon that's filled with helium gas. You're going to be able to kind of squeeze that in a little bit. And the reason for that is that there's a lot of extra space between the molecules of a gas. So extra space between the molecules. Maybe that would look better with a highlighter. So we know, right, the arrangement of the particles in a gas is quite different than that of a solid or a liquid. And there's a lot more distance between those particles. So if we put pressure on a sample, we're able to kind of squeeze those particles closer together. Okay, so some factors that could affect gas pressure. Let's think about a balloon as our example here, is the amount of gas, first of all, which may seem pretty obvious, but if you're inflating a balloon with helium, the more helium that you add to that balloon, the greater the pressure will be on the walls of the balloon. Okay, so the more gas that you add, the greater the pressure will be inside the container. Volume. So we're not talking about volume of gas, we're talking about the volume of the container. So if you are able to reduce the volume of a container that contains a sample of gas, if you can squeeze that gas down into a smaller space, that smaller space is going to have a lot more pressure on the walls of the container. Okay, and then lastly is temperature. So gases are largely affected by temperature increase and decrease, and that's because those gas molecules have a lot of kinetic energy and they're in constant motion. So when you increase temperature, you are also increasing the kinetic energy. And when you increase the kinetic energy of the gas particles, you're also increasing the pressure within a container. So the more, let's say, the more times you can get those particles to strike or come in contact with the walls of the container, the greater the pressure will be. And my little example here is what happens when you take a balloon outside in the cold. This has happened to me before. I've gone and bought balloons for one of my kids' birthday parties, and then you go outside and it's a cooler day and all of a sudden it looks like those balloons shrivel up. But that's only because of that change in temperature. So if you were to get them back inside where there's a warmer temperature, that gas will expand again and your balloons will go back to normal. Okay. So some units for gas pressure, these might be units that you haven't seen before, are the atmosphere, the kilopascal, the torr, short for torricelli, and the millimeter of mercury. And interestingly enough, millimeter of mercury and torr are equivalent to one another. So probably the most common that we'll use would be the atmosphere. And it's important to know this relationship here, that 1 ATM, so 1 atmosphere, equals 101.3 kilopascals. is also equal to 760 millimeters of mercury and 760 torr. And we will use those relationships as conversion factors to convert between units of pressure. So those are important to remember. Standard temperature and pressure. So you have heard STP before. And STP, right? Standard temperature and pressure. You would have heard that last chapter when we talked about converting moles to volume. So the values for standard temperature would be 0 degrees Celsius or 273 Kelvin. So not sure if we have talked about Kelvin before, but that's Kelvin. So Kelvin. And then our values for standard pressure, and remember these are all equivalent to one another, just like 12 inches is equivalent to 1 foot. 1 atmosphere, 101.3 kilopascals, or 760 millimeters of mercury. Okay, and back to our temperature, because you're going to need this as we move forward, to convert between degrees Celsius and Kelvin, right? So Kelvin equals, it's going to be pretty obvious based on the above relationship, equals degrees C, so degrees Celsius, plus 273. And for the gas laws, when we do calculations that involve temperature, your temperatures are always going to have to be in Kelvin. So if you're given degrees Celsius, all you have to do is add 273 to that temperature to convert to Kelvin. All right, so the gas laws that we're going to talk about are Boyle's, Charles, Guy-Lussac, the combined gas law, and the ideal gas law. And the gas laws, really what they do is they look at the relationship between pressure, volume, and temperature of a gas. And if you change one, right, if you were to change the volume, what would happen to the pressure? If you were to change temperature, what would happen to volume? So that's basically the relationships that we're going to be looking at with our gas laws. So what we're going to cover today are Boyle's and Charles, and then you guys will have some practice to work on based on those two laws that we talk about. And they're really based on pretty simple algebra. So let's get started. So Boyle's law, okay, this is our first law, looks at the relationship between pressure and volume. So in order to look at the relationship between pressure and volume, temperature has to remain constant. So you will hear that repeated in the problems when we're going to be using Boyle's law. So temperature remains constant. As the pressure of a gas increases, the volume decreases. So one goes up and the other goes down. And that type of relationship is called an inversely, this will take me a minute, so inversely proportional. Let's try. Cursive, there we go. Inversely proportional relationship. So one goes up, the other goes down, and that proportional means that if it goes up by a factor of two, the other thing goes down by a factor of 2. Okay, so the law is P1 times V1 equals P2 times V2. So P1 V1 equals P2 V2. So if you look at the graph of something that is inversely proportional, right, as our pressure is going down, right, so pressure is here on the y-axis, volume is here on the x-axis. So as our pressure is going down, our volume goes up. And if we take a look at a practice problem, so if we have a balloon that contains 30 liters of helium gas at 103 kPa, so that's kilopascals, so we're given a volume and a pressure, and these are our starting amounts, so volume 1. And I like to do this with the gas loss problems. I like to label what we're given in the problem. What is the volume of the helium when the balloon rises to an altitude where the pressure is only 25 kPa? So our balloon is rising, the pressure is changing. So the pressure has changed to 25 kPa, and the pressure has gone down. So remember that inversely proportional relationship so we can kind of think through what should happen to our volume when the pressure goes down. So if the pressure goes down, the volume should go up. But let's go ahead and plug our numbers into P1, V1 equals P2, V2. And what are we solving for? So let's go ahead and circle that guy. We are solving for V2, right? What is the volume? So let's plug our numbers in. So we have 30 liters um, 103 kPa. Right, and it equals 25 kPa times V2. Okay, so to solve for V2, right, basically we're going to divide both sides by 25 kPa divide by 25 kPa. Okay, cancel that on this side. And then just plug what we have into our calculator. So we have 30 times 103, divide by 25. And we're going to stick with 3 sig figs for this. So I get a V2. And if you want to even look at how your units cancel out, you know that your units that you're going to end with are going to be liters, which makes sense for volume. We get 123.6, so I'm going to round that to 124 liters. So the math for these is pretty simple. Okay, so that's Boyle's law. Boyle's law, P1V1 equals P2V2. All right, Charles' law. So Charles' law looks at the relationship between temperature and volume. So just like we talked about in Boyle's law, in order to look at the relationship between temperature and volume, pressure has to remain constant. So as the temperature of an enclosed gas increases, the volume increases. So this time we have a directly proportional relationship. So one goes up, the other goes up by the same factor. So proportional, directly proportional. But here's the kicker. Just like we discussed, our temperature has to be in Kelvin. Okay, so if we're given temperatures in Celsius, we have to add 273 to them to convert to Kelvin. So the law is V1 over T1 equals V2 over T2. And we'll rewrite that so it looks like a better fraction. Oops. So V1 over T1 equals V2 over T2. And again, those T's have to be in Kelvin. All right, so let's look at our Charles law graph. So as volume is increasing, temperature is also increasing. And this, if you notice, this is a more linear relationship than the Boyle's law graph. And then we will do this example problem here. So a balloon inflated in a room at 24 degrees C. So there's our T1, but remember, we have to convert to Kelvin. So I'm just going to go ahead and do that by adding 273 to 24, and what I get is 297K for our T1. Oh. And then we have a V1, which is 4 liters. Okay, so T1 and V1. The balloon is then heated to a temperature of 58 degrees C. Okay, so that's T2. And I'm going to go ahead and convert that to Kelvin as well to make life easier. So 58 plus 273 is 331. So what is the new volume? We are looking for V2. Okay. All right, so we have V1, T1 equals V2, T2. And we can go ahead, since we've already converted our T's, we can go ahead and plug in our values. So V1, right, was 4 liters. T1 was 297. Okay, equals, we're looking for V2 over 331K. All right, so our temperature went up. We should expect that our volume will go up since this is a directly proportional relationship. Multiply both sides by 331. Okay, cancel that. So V2 equals 331 times 4 divided by 297. Okay, and I am going to round to, since our V1 was in 3 sig figs, I'm going to round our V2 to 3 sig figs. So V2 equals 4.46 liters, right? We're going to use the same units as our original volume. You don't ever want to change that. So 4.46 liters for V2. Okay, so that is your introduction to the gas laws. Boyle's law, P1V1 equals P2V2, and Charles' law, V1 over T1 equals V2 over T2. I hope that helps. And stay tuned for the next video where we will cover Guy-Lussac's law and the combined gas law. Thanks a lot.